Hi everyone, welcome back. So this is going to be part 3 of the cooling tower problem, and in this part we're actually going to solve this out in Python. So if you remember from the last couple of videos, we found dy over dz, dtw over dz, and dtg over dz, and this represents the change in the mole fraction of water in the air, the change in the temperature of the water, and the change in the temperature of the gas. Now we're going to use Python to solve these differential equations as we go down the column. Okay, so first thing we want to do is we want to import numpy. We're going to be using some functions from there for numerical stuff. And we want to import a function from SciPy called solveIVP. And this is going to be from scipy.integrate. So we're going to be importing this function. Okay. So we're going to take a look at solveIVP here. So solveIVP, there we go. So, okay, so solveIVP takes in a function, some span of variables where our integration will take place, some initial values, method, and we're also going to use dense output. But the one we want to focus on here is this function. So if we scroll down a bit, it looks like our function is going to take in two values, t and y, where t is the independent variable and y is an array of the dependent variables. Okay, so we're actually going to need to make our function. So I'm going to call this dy dtw dtg because those are the three differential equations we're trying to solve. And this will take in our independent variable z, and we will make an array of dependent variables, and we'll call it v. And we're going to specify here the first value in that v is going to be our mole fraction. Our second is going to be the temperature of the water. And the third is going to be our temperature of the gas. Okay. So now what we want to do, we want to type these in. So I want to start here with this. So dy, well, so this includes this NW, this molar flux, which is up here, so I'm actually going to start up here with this. So NW is equal to, looks like it was Kc times, well, okay. So we need to define what Kc is. So if we remember from the Lewis relation, if we know what H is or Kc, we can use the volumetric heat capacity to solve and calculate what the other is. So actually given to us is the heat transfer coefficient is 10. So we'll say H equals 10. Now, in order to get Kc, Kc is equal to, Kc would be equal to H divided by the volumetric heat capacity, which is the density of the gas multiplied by the heat capacity of the gas. So we'll have H divided by, we'll call that rho of air, times C, the heat capacity of the air. So now we're going to need to define these. So the density of air is about 1.2. Rho of air is 1.2. The heat capacity of air is, capacity of air. Okay, so this is in kilojoules. We want this, it's 1 kilojoule per kilogram degree or Kelvin. We want this in joules, so it's going to be about 1,000. 1,000. And since we're here, we will do the heat capacity of liquid water and the heat capacity of water in the gas phase. So this heat capacity of liquid water is about 4,190, and for gas it's about 2,000. Since we're also here, I'm going to go ahead and do the heat of vaporization of water, since we'll be using that later, and that is about 40,700. And that's going to be in joules. So it looks like we have H, density of air, and the heat capacity of air, so that is fine. So we have Kc divided by RT. I'm going to pull RT out. So divided by R, we're going to need it to define R. We'll do that in joules. Okay, divided by T. This is going to be the temperature. This will be, what is this? This is the temperature of the, what temperature would it be? This would be the temperature of the water. Well, would it? Concentration of water at the surface. Well, here's what I'll do. We're going to need the temperature of the water going in and the temperature of the air going in. And I believe these are given to us. Hot water enters from the top at 70 Celsius. So T water in equals 70 Celsius. We're going to add 273 to convert to Kelvin. And it looks like air temperature of 25 Celsius. 25 plus 273. So this is the temperature of the water. Is that correct? Yeah, that must be correct. And then from there we'll multiply by the, so this is going to be the saturation pressure of water at the temperature of the surface of at the temperature of the water. And to do that, or to get that, we're actually going to have to use the Antoine equation. So what we'll need here is we need to set up an Antoine equation. So this we'll call this. This will give us the pressure of the water at some temperature, and it will return. I actually have the Antoine equation pulled up here. So the way that this works is that we will have some temperature, or some temperature here, and some pressure, and we have this A, B, and C, and these depend on what we're actually working with. So, for example, between water and ethanol, the A, B, and C would be different. It depends on what component we're talking about. So if we were to solve this for pressure, it would actually look something like this. That's down here. So it looks like we have 10 to the power of A minus B divided by C plus our temperature. It looks like our temperature is in Celsius and our pressures, it gives us a pressure in millimeters of mercury. So I'm just going to copy and paste these over. So we have 10 to the power of A minus B divided by C plus temperature. And this temperature, our temperatures down here are in Kelvin, but this temperature needs to be in Celsius, so I'm going to subtract 273. Okay. Is that enough? Yeah. And since it gives us an answer in millimeters of mercury, I'm going to divide by 760. I'm going to multiply by I'm going to convert that from millimeters of mercury to pascals. Okay, so from here, we can type in PW at the temperature of the water minus the partial pressure of the water, which is going to be the total pressure times the mole fraction. So we need to define our pressure. It's going to be atmospheric pressure, which is there in pascals. Okay, so that's our NW. Now we need to type in our first differential equation, which is going to be dy. So dy equals, it's going to be negative molecular weight times A over G. Okay, so we have a few things we need to define here. So first A. A is given to us, specific area of 5. Okay. Now molecular weight. So what I'm going to do is I'm going to say the molecular weight of air, well, water first, equals 18. We want that in kilojoules, so we'll go E to the minus 3. The molecular weight of air equals 29. But for this equation in particular, this G that we're looking for is going to be this M is going to be the molecular weight of the gas, not the air or water by itself, but the gas combined. Same thing with this G, it's going to be the total flow rate. So if we look here, we need to figure out how much air is going in. So we know how much water is going in. Hot water has a flow rate of 0.5 kilojoules per meter squared per second. So we'll put that in. And we'll call that L for the flow rate of the liquid water. But we need something about the air. Air enters from the bottom with a velocity of 5 meters per second. So we'll say velocity equals 5. And if we remember from the last video, if we have the velocity of the air, we can actually find what the flow rate is from that. So we will multiply by the pressure and the molecular weight divided by R divided by the temperature of the air going in. So we will have the velocity of the air. Well, this will be the flow rate of the air. Oops. So this is going to be the velocity times pressure times the molecular weight of the air divided by R divided by T of the air that's going in. And I'm going to move these up above here. Okay. So from there, we can get the flow rate of the water, which is equal to the flow rate of the air times the molecular weight of the water divided by the molecular weight of the air, but then we multiply in the mole fraction of the water. But this actually depends on what Z is, and because of that, we need to include this inside our function for the differential equations, because it will change as we go down the column. So we'll have the flow rate of the water equals the flow rate of the air times the molecular weight of the water divided by the molecular weight of the air times y divided by 1 minus y. That's our expression. And now we can say that G, the flow rate of everything, is equal to the flow rate of the water plus the flow rate of the air. But now we need the molecular weight of everything, and luckily we also already figured out what this is. This is going to be the flow rate of the mass flow rate of the air and water divided by the mole flow rate of the air and the water. So we will type that in here. So M equals, so the mass flow rate, so that's going to be G air plus G water divided by G air divided by the molecular weight of the air, that's going to be the moles of air, plus G water divided by the molecular weight of the water, that's going to be the moles of water. Okay, so that is all we need there. Scroll up. And we just multiply by the molar flux. So times molar flux. Okay, so now we're going to move on to the change in the temperature of the water. This will be equal to A divided by L divided by CL. So A divided by L divided by CL. So that's going to be the heat capacity of the liquid water. We said that was CWL, the heat capacity of water as a liquid, times, and then we have the heat transfer coefficient times the difference in temperature between the gas and the water. H times, so this will be Tg minus T water. Then we will subtract the heat of vaporization of water times the molar flux. And that should be good. I want to make sure we have everything here defined. Yep. Okay, so then finally we have the change in the temperature of the gas, which is our last differential equation. AH over GCG. So this is A times H divided by G divided by CG. Now, this CG is going to be the heat capacity of the gas, which includes the air and the water. We know the heat capacity of the air and the water, but not when they're combined. But we actually have an expression for this down here that we found in the last video. So I will type that out. So CG equals, so this is going to be C air plus G air, or times, plus C water times G water, and then we'll divide by the total flow rate of the gas phase to weigh it. Okay, and then finally, we'll multiply by the temperature difference. Just like that, check to make sure that that is correct. Okay. And I think we're good to go. We just need to we'll return the variables in the order that we give them. So we'll return dy, dtw, dtg. Okay, so that is our function for our differential equations. So we're going to put that in here. So dy, dtw, dtg. Now our span of our, it's just going to be our limits on integration. So we want to go from 0 to the height of the column, which is 20. And then we're going to need our initial values. So what we need to do is go up here. And if we remember from the last video, we actually said our initial value z equals 0 is going to be at the top of the column. So our initial conditions are going to be the water going in temperature, the temperature of the gas going out, and the mole fraction of the water in the gas going out. So we don't know what these two are. We don't know what the temperature of the gas out is and the mole fraction. So we're going to have to come up with guesses for that. So we will call a guess temperature of the gas out, guess. I'll put a G there for guess. And we will have mole fraction going out, guess. So we'll say that that's equal to the mole fraction going in, multiplied by some small number. We'll just maybe guess that it won't change a whole lot. And for this temperature going out, we'll say that that's equal to the temperature of the gas in, which we actually labeled that as temperature of the air going in. And we'll just add on 5 degrees, just a small value. So then for these initial guesses, we want to put them in the correct order so that our mole fraction going out guess, our temperature of the water going in, and our temperature of the gas going out guess. Finally, we want to do method equals, we're going to use Radeau for our method, and this is just how the program actually solves the differential equation. And finally, dense output equals true. Okay, so what I'm going to do is run this and hope it runs. So we have CW is not defined. Oh, right, so this is going to be the CW gas. And what we have here KCRTW. Y. Let's see, what is the issue here? Unsupported operand types. So I must have something in incorrectly. So KC equals H divided by that divided by times that. Okay. R. Okay, well, R is correct. TW. TW is right. Okay. Let's see here. So Y out equals. Okay, I'm a little bit confused here. We're gonna go ahead and do this. Restart and run everything. Okay, there we go. There we go. Yn is not defined. Right, okay, there we go. So the mole fraction of the water going in, what they give us is the relative humidity of 50%. So to go from relative humidity to mole fraction, what we're going to need is, we're going to need to use the Antoine equation. So we'll say Yn equals, we're going to need to do the Antoine equation at the temperature of the water, of the air going in. Yeah, so this will be, let's see, this is PW. So this will be PW at the temperature TAN. Oh, okay. Multiplied by the relative humidity. And then we need to divide by the total pressure. Oops. Okay. So that's good. No, this is not good. Height is not defined. Right, okay. Height equals 20, because our 20 meter tall cooling tower. Okay. Okay. Go back through one more time just to make sure there's no errors here. Make sure we didn't forget anything either. Uh, huh. Tea water in 70. Huh. What is... So these are actually different numbers than I've gotten before. So I wonder if that's because there we go. So this would actually be the temperature. So in our let me see, in our molar flux, which is right here, this temperature, I put this in as the temperature. Can I? Yeah. So this temperature right here, this RT, I put that in as temperature of the water, which is not correct. That would be temperature of the gas, of the temperature of the gas phase, because when we're actually well, because the temperature of the gas phase, well, the temperature of the water would actually be included. Let me see. Would actually be included here, which we did correctly. But this RT would be for the gas, not the water, not the liquid water. Especially since we have gas constant here. Okay, so this is better. So this is actually our answer. Well, this is our answer. This thing called SOL. That's where our answer is. So what we can do is we can type in SOL at any number, and it will give us the values of our differential equations at that number. So what I'm going to do is go up here. I'm going to define something called, well, I'm going to say this is z-plot, and this is going to be np.linspace. This will give us an array of numbers between 0 and 20, which will be the height of the column. And it will give us 21 values between that. So in this case, it will be every integer. So what I'm going to do is go down here and say that solution equals solve our IVP dot SOL, which will access these SOL values. So this dot SOL means take the number, take the number here, which is going to be z-plot, and give us the values of the differential equations at that z value. So what it will give us is, well, okay. Well, here. What this will give us is an array of arrays, basically. So we have an array here, an array here, and an array here, all inside one big array. And what this first array is there's 20 values. So those are our numbers, 0 through 20. And at every value, at every value, the array will give us dy, which is in the first array, dtw, which is in the second array, and dtg, which is in the third array. So it gives us the values of the mole fractions and the temperatures at every z value that we give it. So this is going to be when z equals 0, this first number, and this last number is going to be when z equals 20. So if we look back here at our picture, z equals 0 is up here, z equals 20 is down here. So what we know is that when z equals 20, the value of y should be It should be, well, let's see what it should be. It should be about 0.016. But it looks like here we're getting about 0.006, which is not correct. So that means of course our guesses are wrong. So what we need is to change our guesses to make these final values line up with this and our temperature of the gas going in, or I think temperature of the air going in, which is 298. And it looks like down here we have about 302, so that's off as well. So the way we're going to do this is we're going to use a root solver. So root, and actually I'm going to need to import from scipy.optimize, import root, run that. And root is going to take in, well, let's see if it pops up, a function, which is a vector function to find the root of, and our initial guesses. So what we're going to need to do is come up with we're going to need a function here, a new function. I'm going to call it f, and it's going to have an array. I'm going to call the array v2. And I'm going to specify that, so we're looking for the mole fraction of what's going out. So that's going to equal the first value in that array. And the temperature of the gas out equals the second value in that array. So then from there, we have these same differential equations, but instead of these guesses, it will actually use the values from this array. We'll need to pop that in there. And what we want to return is, we want to return things that are equal to, well, we want to return those final values from the array that we were just looking at. So we want to return, well, let's see. So we want to return SOL, and then the first array in the group of arrays, and then this -1 specifies that it is the last value in that array. And we know that that should be equal to the mole fraction of the water in the gas phase that's going in. So if we say minus yn, then now this is returning something. This will be returning something that's equal to 0, because we want this to equal this. And so it's trying to return 0, and that's what the point of the optimize function is, or the point of the root function. So we'll do the same thing for the temperature of the gas. So this will be 2, -1 minus temperature of the temperature of the air going in. And those are defined up here. Yn, temperature of the air going in. Okay. So now we will use root, function is f, and our initial guesses are y out guess and tg out guess. So I will go ahead and run everything. Okay, v is not defined. right? This needs to be v2. Oops. Try it again. Okay. So it gives us this stuff here. This is actually our answer. So what this means is that when the temperature, when the mole fraction, well, this means that in order for our differential equation to be correct, the mole fraction of the water in the air going out must be equal to 2.5 times 10 to the negative second, and our temperature of the gas going out must be equal to 300 Kelvin. That's what this means. So that's our answer, and yeah, we used Python to get the answer. So now actually what we want to do is graph this. So what we're going to need to do is we're going to graph it from 0 to 20. So our x values are going to be every point on this plot of 0 to 20. So our z plot. And our y, or our y values for our plot, or our graph, it's going to be the values of the differential equations at the point at whatever z value is from this z plot. So what we're going to do is we're going to set up figure, and we'll say that's equal to, well, actually what we need to do is hop up here and import plotly. So this will give us functions to make our plots. Do this correctly. Oops. So this will be from plotly dot subplots. Import make subplots and import plotly dot graph objects as geo. Okay, so we'll do this. Figure equals make subplots. We will have one row and 3 columns. And we're going to do figure dot add scatter. So now we're going to add in our lines. So our x is going to be equal to our z plot. So we'll take 20 x values for each value on our z plot. Now our y is going to need to equal so our SOL value at every z plot value. Well, it's going to need to be from our SOL. So this first line is only going to be the mole fractions. So if we remember from those set of arrays, we had 3 arrays. The first array is going to be our mole fractions of water, so that'll be 0. And then for our it's the first array and then every value in that array. So we'll put the colon there for every value in that array. And then we'll say name equals y water. Well, H2O. We'll see if this works. So I'm going to do this again, restart and run everything. And we should run into an interesting problem here. So it tells us that SOL is not defined. When we did define it earlier, I mean, it's right here. But the reason for this is that our solution is inside of this function. So this function, f, is what we use for our root. what we use to solve and find the correct values. But SOL is in there, is inside that function. So when we try and access it from outside of the function, we can't see it. Python can't see it. So the way we get around this is we're going to go up here and we're going to say SOL. We're going to set a variable SOL and say it equals none. It just means there's nothing, but it is defined. There is a variable SOL. Then we will say here global SOL, which means that when we use SOL within this function, it also changes the global SOL up here to the same value. So now when we run everything, it will save the final value of SOL is going to be our solution. And we'll be able to access that solution from outside of the function. So there we have it. So the mole fraction starts up here when z equals 0, so this is actually where it ends. And then it goes down to here, where it equals 0.016. And we can test right here. We know that that's the mole fraction of the water going in. 0.016, 0.016. So that is correct. And that's actually about it. I'm gonna pull up this real quick. So again, this right here, this means our x values are every value on our z-plot, so it goes from 0 to 20. And for our y values, we go SOL at 0, or it would be SOL, so it's going to go into this array here, SOL, and it's going to take the 0th array that's part of that array. So again, this is array 1, array 2, array 3. Array 1 contains every mole fraction of water in the air. Array 2 contains every temperature of the water, and array 3 contains every temperature of the gas. And it's going to go through and it's going to take all of these. The colon means grab everything in this first array, and that's what it puts on the y-axis. So that is how we make this. So now we just have to do that 2 more times. So I'll copy and paste. And the only thing we need to change is that instead of grabbing from the first array, we grab from the second array and the third array. And this will be the temperature of the water, T H2O, and this will be the temperature of the air. Well, temperature of the gas. And there we go. Although this is this is one useless graph. Right. So mole fractions are between 0 and 1, but these temperatures are at 300, 350 Kelvin. So of course, that's useless. So what I'll do is I'll say row equals 1, column equals 1. From here I'll say row equals 2, column equals 1. And here I'll say row equals 3, column equals 1. So it'll put these each one in a different row. Okay. Let's see what happens. Enlist index out of range. Oh, okay, so we have 1 row and 3 columns, so 3 rows, 1 column. That should fix it. And there we go. Although this is still pretty bad. So actually, I'm curious what would happen if we did this, 2, and then for column, we counted up on the columns. Oh, okay, that's really nice. Okay, so there we have it. On this first graph, we have the mole fraction of the water. In the second graph, we have the temperature of the water, and then the third graph, we have the temperature of the gas. So this is from the top of the column to the bottom of the column, top to bottom, top to bottom. And actually, I just want to check. We already checked the water coming out, it's 0.016. But the temperature of the gas out, or the temperature of the gas going in, 298.15, which means that if we go down here, we should get to 298.15, and we do. We see 298.15 right there. So this is correct. This is exactly what we're looking for. Okay, so this is the whole problem. So just to recap a little bit, we had a cooling tower with water going in, water going out. We had gas going in, gas going out. This gas had some water, some moisture in it. From there, we were actually able to, from there we were able to come up with differential equations. First, we looked for the change in the mole fraction of water in the air over the change in z, which we set our positive z direction to be down. And the way we did that was by setting up a bit of a mass balance here, where we said the change in the water flowing is equal to the mass flux of the water. And then from there, we were able to come up with this first differential equation. Then we looked at the change in enthalpy of the water, and we were able to set up an expression for that. And from there, we could come up with the change in the temperature of the water, the differential equation for that. And then finally, we looked at how the change in enthalpy of the water and the gas, how they relate, and we found that the change in the water, the enthalpy of the water is equal to the change in the enthalpy of the gas. And from there, we were able to set up an energy balance for the gas and come up with our third differential equation. And then from there, we just went over to Python. We solved these differential equations, and then we used a root solver on Python to find what values make the differential, or what initial values give us the correct final values after solving the differential equations. And then from there, we just graphed our answer, and this is what we end up with. So that's actually going to be it for the cooling tower problem. So yeah, thank you everyone for watching, and I will see you around.